Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 4, which is all about covalent bonding and simple molecular compounds. So the term molecular might be somewhat new, maybe you've heard it before, but molecular actually refers to, or molecules actually refer to covalent compounds. So sometimes you'll hear me talk about ionic compounds versus molecular compounds or versus molecules, right? Molecular compounds or molecules are specifically covalent compounds. So different, just a distinction there. But what are covalent bonds? So we talked about ionic bonding in the last chapter, and we said when electrons can be transferred from one atom to another, so that both atoms have those 8 valence electrons or a full valence shell. Remember that for hydrogen and helium, a full valence shell is just 2 electrons, and that's just because the 1s subshell can only hold a max of 2, so they're okay just having those 2 electrons. So for hydrogen, though, right, hydrogen, these are 2 hydrogen atoms, they only have that 1 valence electron each. So what hydrogen says is, you know what, like I really want to have a full valence shell. And since hydrogen is so abundant on Earth, what will often happen is hydrogen atoms will come together and say, you know what, let's just share our valence electrons and form what's called a covalent bond. So these 2 atoms will come together and say, let's share these valence electrons, and then we can both be happy. And this is why we actually find hydrogen as H2 in nature, is because usually when you find hydrogen, it's bonded to itself because it's so much more stable to do that. Remember, hydrogen is one of our Hofbrinkels. It's one of our diatomic molecules. Okay, so it'll like to bond to itself. And this is why it's so it can share those electrons and be stable like helium, right? Which is our noble gas with a full valence shell. So this is different, right? This is different than when we are losing or gaining electrons, right? Covalent bonds are sharing electrons. And when we share those electrons, those 2 electrons that join together in those atoms, that's called a covalent bond. And we would also call the electrons in that covalent bond, the ones that are participating in the bonding, we'd call those the bonding pair of electrons, because there's 2 of them. And we would also call, now this whole thing, this H2, we would call that a molecule of H2. And that's the smallest part of a compound that retains the chemical identity of that compound. So what do I mean? When you look at a glass of water, if you zoomed in really, really far, what you would find would be water molecules. And the smallest of that would just be 1 water molecule, right? Because water is a covalent compound. Those hydrogens are sharing electrons with oxygen, and we'll talk about that. All right, so what are kind of the properties of these covalent compounds? So it turns out that covalent compounds or covalent bonds are actually less strong, or they're weaker, than something like ionic bonds. And the reason for that is that with ionic bonds, we're creating this kind of difference in charge, right? So for something like Na1+ and Cl1-, that difference in charge is really, really strong at keeping those 2 ions together, right? Because they really want to be neutral. So they're going to kind of stick together as much as possible and not want to leave each other's side because they have that difference in charge. So that makes them kind of a stronger bond. Whereas covalent compounds, they don't have that difference in charge that's kind of fueling that strength in a bond. There's no attraction between those other neutral molecules like there is for ionic compounds. All right, so as a result of this, right, covalent compounds generally have lower melting and boiling points than ionic compounds. What does that mean? That means that you have to add less energy to get a covalent compound to boil than you do for a ionic compound. For ionic compounds to get to get them to melt or boil, you have to add tons and tons of energy in. So their boiling points tend to be really high. All right, so then just like we had a specific naming and way of writing formulas for ionic compounds, molecular compounds also have a kind of some special rules. So remember that molecular compounds are between nonmetal plus nonmetal. Okay, so they're all nonmetals. If you have a metal in there, remember that's ionic. So all nonmetals for molecular or covalent compounds. And what we're going to do is we're going to name the nonmetal that's closer to the lower left corner of the periodic table first. So for instance, right, for an example, we have something like CO2, which we're familiar with, right, carbon dioxide. The reason carbon comes first is because carbon is closer to the left than oxygen. Okay, so we say carbon dioxide instead of oxygen, I don't know, oxygen first and then carbon. All right, so now we got to talk about how we actually name these molecules, because again, there's a specific way that we go about this. So covalent compounds, typically in this class, we're going to be naming these things called binary covalent compounds, which means they consist of kind of two elements. That doesn't mean two atoms, it just means two different elements. So here we've got 3 atoms total, right? 1 carbon and 2 oxygens, but we have 2 different elements, carbon and oxygen. Okay, so we typically won't stray too much from that in our class. So the way that we do this is the first element in the formula is just listed using the name of the element. So just like we do with ionic compounds, the first element that's in our formula is we're just gonna give it its regular name. So in this case, right, we have carbon dioxide. We just say carbon first. And then for the second one, you'll notice this ending IDE probably looks pretty familiar. It's just like with ionic compounds. The second element always has that ending IDE. Okay, that ending IDE. Okay, so carbon dioxide instead of oxygen. All right, but what you'll notice is different from ionic compounds is that we have this prefix here, di. So with molecular compounds, when these molecular compounds form, it's not like with ionic compounds where they have to form in a specific ratio in order to cancel out those charges. For molecular compounds, they can form in different ratios. So, right, I've used this example in class quite a bit, but CO2 versus CO, these are very different molecular compounds, right? CO2 we breathe all the time. Carbon dioxide, but CO, what's that? Yeah, carbon monoxide, right? A lot of us have CO meters in our house. I hope you do. We don't want to breathe that in, right? So very different compounds. But if we called both of these carbon oxide, right, we wouldn't know which one we had. So we have to use these prefixes to tell us how many of each atom we have for these molecules. So how do we do this? We have to specify the number of atoms that are in molecules. There's an exception, of course, as there always is in chemistry. Mono for 1, right, for the prefix for 1, is only used for elements that are not the first element. So again, my favorite example, CO2. We don't call that monocarbon dioxide. If we just say carbon for our first atom, just for the first one, it's assumed that there's only one. So you don't have to say mono in front of it. So it's just carbon dioxide. And because there's no other prefix in front of it, we just assume that there's only one of that atom. So that's one of the exceptions. After that, right, if you have 2 atoms of a specific type in a compound, you get the prefix di. So that's why we have dioxide for oxygen, right? Carbon dioxide lets us know we have 2 of those. There's also tri for 3, right? Tetra for 4, penta 5, hexa 6, hepta 7, octa 8, and nona 9, and deca 10. Okay, so all of these you need to memorize. Okay, I would recommend making flashcards. A lot of them you'll get pretty used to just naming these a lot. We're going to do lots of practice, but it is something that you need to memorize. So Some of these I have a little trick for memorizing them. So I like to think of like a triangle, like 3 sides, right? Triangles have 3 sides. Penta, I sometimes think of pentagon, right? Pentagon has 5 sides. Hexa, think of like a hexagon, has 7 sides. Octa, like an octopus, has 8 legs, right? Deca, I like to think of like a decade, 10 years, right? So these are just some kind of memorization tips that I've used in the past. But let's try this out. So we're going to name this following compound. And remember, right, the first thing I do anytime I'm given some kind of compound formula is I go, hey, is this ionic or covalent? Because if it's my goal to name this compound, it matters, right? If it's ionic versus covalent, because the naming schemes are slightly different, right? For molecular or covalent compounds, we have to show that prefix. So what I would do then is I would say, all right, well, do I see any metals? If I do, right, that's ionic. So ionic equals metal plus nonmetal. And covalent equals nonmetal plus nonmetal. And you can have more than one, right? So what's this one? Yeah, this one's covalent because we've got a nonmetal here and a nonmetal here. Okay, so what would we call this? Take a stab at it. So we want to just list the first one, so nitrogen, right? Just what we see on the periodic table. And then for oxygen, we know we're going to have oxide, right? Ending IDE, right? Just like we do with ionic compounds. But if I just said nitrogen oxide, the compound for this, the compound formula would be NO. And that's not what we have, right? We have 3 O's, and we have to show that with these molecular compounds. So what goes here for our prefix to let us know that we have 3 oxygens? Yeah, trioxide. Trioxide, because we have 3 of them. All right, so practice these, and then we'll come back and talk about them. All right, so we're going to name these, and we're told that these are all molecular, but you could also double check, right? Non-metal, 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 non-metal. Okay, so these are all covalent compounds. All right, so for the first one, just listing our first atom here. What is our first atom? Yeah, phosphorus. Now, what comes next? Something I know with chlorine, but chlorine gets the ending IDE, right? Because it's the second element that's listed. So we give it that IDE ending. And then what goes in front of chloride? Penta. Yeah, a little bit weird. Like pentagon, 5 sides, right? Pentachloride. So phosphorus, pentachloride. And this looks like a capital. It's actually a lowercase. Okay, something like that. All right, next one, carbon. Just listing the first one. And then I know I'm going to have fluoride. Fluoride instead of fluorine, fluoride. And then what goes in the middle? Yeah, tetra. Tetra. A little bit weird, but tetra. Because we have 4 of our fluorines. All right, and now the next one. Notice in these first 2, we didn't have anything here because we only have 1 of them, okay? So we don't have to put anything there. But for this one, we do have 2 nitrogens. So now you need to indicate how many nitrogens you have. So what's your first prefix going to be? What goes in front of nitrogen? Yeah, dinitrogen. Di goes first because we have 2 of them, right? All right, and then we'll do, I don't know, we'll do green for the next one. So how about for oxygen? What's the prefix there? Yeah, pentoxide. Yeah, it's a little bit weird when you have a vowel here. You're going to drop that A in penta. So you don't want to put 2 vowels next to each other. It just sounds funny, so we drop it. So pentoxide instead of pentaoxide. Okay, just a mouthful to say that. Oops, let me put that in green. Pentoxide. So instead of pentachloride, right, with the A there, because this is not a vowel, that's C, we just drop that A, pentoxide. I probably wouldn't mark you wrong for writing it like that, but I would make a little note so that you wouldn't do it the next time. All right, now our job is to write the molecular formula from the name. So we're kind of going the opposite way. So now I'm telling you the name and you want to write the molecular formula. Well, I know I have sulfurs and oxygens, and now my job is to just figure out, well, how many? So how many sulfurs? Yeah, just one. Remember, for the first atom, you don't have to put mono in front of it if you only have one. So just S, right? Just listing sulfur. And then for oxygen, how many oxygens? Yeah, di is 2, right? So this has to be 2 here. SO2, sulfur dioxide. Just like H2O, the fancy name would be dihydrogen monoxide. So if you want to be cool at your next, party that you go to or whatever, you can be like, can I have a glass of dihydrogen monoxide? And everybody will think you're really smart. But they'll also look at you funny. All right, the next one, carbon tetrachloride. So I'm going to list, right? We got carbon first. How did I know to put carbon first? Yeah, we said it first, right? So carbon comes first. It's also more to the left on the periodic table. And then what about for chlorine, right? Chloride, so I know I have Cl. How many? Yeah, 4, tetra. And then for the last one, phosphorus and bromine. Looks like I only have 1 phosphorus, but I have 5 bromines. So PBr5.